Projectile motion. All right, so there's 3 videos for this part of the unit. The first one's concepts, the second one is a couple example problems, and the third part is some tips and tricks. So the first thing I want you to consider is if you fire a gun with a muzzle velocity of 1,000 feet per second, and you drop a bullet at the same time, which one will hit the ground first? Now, this is, of course, assuming there's no air resistance, but I want you to think about it for a moment, and we'll come back to this question. So if I wanted to swim across this river, and let's just say it's 100 feet wide, or kayak, I guess, across the river, and I want to know how long is it going to take for me to cross the river. If it's 100 feet and I'm going 10 feet per second, it's going to take 10 seconds. But now if the river's moving at 200 feet per second, how long will it take you? Now, if you said 10 seconds, you are correct. Because I'm going to aim myself straight across this river. Now, in reality, if I aim myself straight across the river, I'm going to be swept downstream at 200 feet per second as well, which will result in me ending up over there. But it will still only take me 10 feet per second because I'm only need to try to swim straight across the river. So here's an animation of the same thing. You'll notice that in the X direction, the boat is moving at the same speed the whole time. The difference is that when there is a river pushing the boat's going to end up farther upstream. So it's not intuitive because in real life you're trying to aim for a specific point on the shore. But if you don't care where you end up on the shore, then you only aim at the other side and you just keep swimming. So in this case, if it takes you 10 seconds to get across the stream, I will be swimming 10 feet per second across the stream, but also moving 200 feet per second downstream, which will result in me ending up 2,000 feet farther to the right. Now, if I wanted to instead cross this river and go straight across, that would not be possible because I would not be able to swim fast enough upriver at an angle. So how does this relate to projectile motion? This is a little cartoon. It says, I shoot an arrow into the air. It falls to earth and I know where. Poetry for physicists. So there's this video, and I would like you to watch it if you're watching this at home. Otherwise, we will watch this in class. It is a bowling ball versus a feather in a vacuum chamber. So take a look at that and then come back to this video. So with projectile motion, we're going to assume 2 things. The first is that acceleration of gravity on Earth is 9.8 meters per second. So what you saw in that video is that both the bowling ball and the feather accelerate and move together at exactly the same speed with exactly the same acceleration because there is no air resistance. Now, I know that in real life there is air resistance, but we're going to assume that that is 0 for the sake of this class because air resistance is very, very complicated. And that also goes along with the air resistance is going to be negligible. So sometimes it's like, what is free fall? Well, basically it's any time you throw or drop something and there's nothing pushing it while it's moving, just the force of gravity pulling down on it. So once you throw it or drop it, it's just going to keep going and speed up just because of gravity. Things that are not in free fall would include like a rocket, somebody that's parachuting where there's significant air resistance, a frisbee, Superman, anything that's getting pushed or pulled on while it's flying in the air is not in free fall. So here we have a cannon. If we shoot this ball sideways, it's going to keep moving at a constant speed. So we've turned off gravity, and it'll just keep going. There's nothing pushing it to make it go faster. There's nothing pushing it to make it slow down, because again, we are in the world of perfect physics where there is no air resistance. And so it's going to keep going that way at a constant speed. Now, if instead we drop it, and there's only gravitational force acting on it, so we just drop the bowling ball, we're going to notice that it gets faster and faster as it falls down. So the distance between these pictures is going to get bigger because as it goes faster, it's going to go farther. Now, if we put these two things together and we launch it with gravitational force or with gravity, what we're going to do is we're going to put these two things together. So we're going to combine the horizontal and vertical. So here we have horizontal and vertical, so then that's where it's going to end up. And same thing with this one and this, and again, and again. So horizontally, it's moving at a constant speed, and vertically, it's speeding up. And the result is projectile motion. So that means that we're going to have to deal with these things separately. So here's another animation. We have the x direction moving at a constant speed. The x direction's not changing, but your y direction is getting faster and faster as it falls because in the y direction it is speeding up. Now, it doesn't not matter if something is dropped or if it's thrown. Any object, if it goes to the same height, you'll notice that at each second, it is still at the same height, regardless of what's happening. So sometimes it'll be easier to consider an object as if it was dropped from the highest point versus thrown up and back down. And so at this highest point, that's where your velocity in the y direction is 0. So the motion on the y-axis is independent of the motion on the x-axis, meaning that it doesn't matter what's happening push or pull wise in the y direction, the x-axis is going to be independent of that. And in the y-axis, we have free fall motion, and in the x-axis, we have a constant velocity. And we're going to have a constant velocity in the x direction because there is nothing pushing or pulling on it in the x direction. So what you'll do is you're going to make a list of variables. You're going to have the x's and the y's. So you have x naught and x. So your starting position, your position at some time, your starting velocity in the x direction, your ending velocity in the x direction, your acceleration in the x direction, and time. And then you have all the same things for the y direction. So what's always true in projectile motion on Earth? Well, the first one is going to be that our acceleration in the x direction is 0 because we are not going to have anything pushing or pulling on it in the x direction. We also know that on Earth, our acceleration in the y direction is negative 9.8. And I make it negative because I like to say down is negative and up is positive. If you want to switch it, you have that ability to, but if you want your answers to match my answer key, then you'll want to make sure that downwards is always negative. And then the other thing to notice is that I have time listed on both of these, but the reality is that time must be the same. You cannot have the time it takes for a basketball to take 2 seconds to fall in the x direction, but 3 seconds to fall in the y direction. That's ridiculous. And then often we will make either x naught or your starting position, or your final position, just regular x, 0. Because if you're going to measure the distance that something goes, it's easiest if you start or end at a height of 0 or at a position of 0, just because that's the way we do measuring. And then if you have an object that is dropped, if it's being dropped and not thrown, that means that your starting velocity in the y direction is 0. All right, so we're going to go back to this. On the horizontal axis, if this is our equation, now we know that v naught x will be something, but our acceleration in the x direction will be 0. And I like to start with the starting position at 0, so that will also be 0. And so we're left with the position in the x direction is equal to whatever our x direction velocity is times time. And we can do the same thing for the vertical. And here in the y direction, our starting velocity, v naught y, is going to be 0 because we're launching it horizontally. So if it's launched horizontally, that means v naught y is going to be 0. And then I will make this starting position, or the ending position, 0, because that's the height of 0. And so we're starting up here in positive land and we'll end at a height of 0. So then that simplifies to this. So if we go back and we reconsider our gun bullet scenario, a gun with a muzzle velocity of 1,000 feet per second, when we shoot that bullet and we drop a second bullet at the same moment, at the same time, they will hit at the same time. So it does not matter how fast you're going sideways. Vertically, it will behave exactly the same way because there is no air resistance. So let's do a few conceptual questions. We're going to hit a ball and they both are going to go to the same maximum height, but ball B is going to land farther away. And I want to know which ball spends more time in the air and which one has a greater launch speed. Well, one thing to remember is that the height is what is going to determine the amount of time. So if they go to the same height, that means you're going to have the same time in the air. And if they have the same amount of time in the air, if B goes farther, then it must be going faster. So the time of flight depends only on the vertical component of the initial velocity. In this case, the vertical component is the same. So both balls reach the same height, so they will spend the same time in the air. And since ball A has a shorter range, the horizontal component of its initial velocity must be less than that of ball B, so ball A has a smaller launching speed. Now for this one, which ball spends more time in the air? Now ball B is going higher than ball A, but they both are starting and ending at the same position horizontally. Well, here, ball B goes higher in the air, and if it goes higher, that means that it must spend more time in the air. And if and ball B also needs to have the greater launch speed, because in the y direction, if you just think about the y direction, in order to get it to go higher, it must also go faster. So again, the time of flight depends only on the vertical component of the initial velocity, and B goes higher, so it must spend more time in the air. Both balls have the same range. We know that 45 degrees gives a maximum distance range for a given speed. Equivalently, 45 degrees is the angle required for the smallest launch speed to achieve a given range. The closer the launch angle is to 45 degrees, the closer the launch speed is to the smallest speed. The launching angles of both balls is greater than 45, but notice that ball A's launch angle is closer to 45 degrees than ball B's, so ball A has a smaller launch speed of the two. Next, we'll talk about examples and calculations.